In this section, we will find volumes of solids. Now we know how to find the volume of a rectangular solid, of a cylinder, of a prism. The volume of a prism is the product of the area of the base times the height. The height is perpendicular to the base. Now, suppose we have a solid that doesn't look like any of the well-known geometric shape that we have the volume formula of, and we are interested in finding the volume of this solid. Suppose that this solid lies between x equals a to x equals b. We can estimate the volume of this solid by slicing this into many pieces. Each of the slice has an area a sub x, depending on where x is. We slice the solids into n slices. Each has a width of delta x, which is b minus a over n. In theory, the widths don't have to be the same, but in practice we use the same width. So the volume is the area times the thickness. So the total volume from A to B is the sum of all of the volumes from I equals 1 to I equals n. Using sigma notation, we add up all of the volumes from I equals 1 to I equals n. But each of the volume Vi is computed by the product of the area of the base times the thickness. But we recognize that at n goes to infinity, this is the definition of the definite integral, since it is the Riemann sum. So the volume is the integral from a to b, a of x dx. But it's only true if a sub xi share the same formula for all I. Each of the slices in this case is called a cross-section. Now notice that the area of the cross-section in this case is the area of the rectangle length times the height. And so the volume is the length times the height times the thickness. In the integral, the delta x will become dx, so L and h needs to be expressed in terms of x. So if S is the solid lies between x equals a and x equals b, and if the cross-sectional area of S is a sub x, and a is the continuous function, then the volume is the integral from a to b of a of x dx. The steps in calculating the volume of a solid involve sketching the solid and a typical cross-section, find the area of the cross-section, find the limit of integration a and b, and integrate the area with respect to the variable x or y. Now if the thickness is delta y, then the area needs to be expressed in terms of y, and the limit of integration would go from c to d. Let's confirm the volume formula we just discussed. We know that the volume of a sphere is 4/3 pi r cubed. R is the radius of the sphere. But we also know earlier that the volume is the integral from a to b of the area dx, where area ax is a function of x. To do this, we're going to slice the sphere into many slices. Each of the cross-section is a circle of radius r. Now this is the circle inside the sphere, so the radius r is called the little r, not the capital R. The capital R is the radius of the sphere, and the little r is the radius of the cross-section, which is also a circle. The area of this cross-section is pi r squared because it is a circle. If we slice the solid perpendicular to the x-axis, then the radius of the cross-section is y, as the diagram shown. So r equals y, and y is related to x and capital R by the Pythagorean theorem, where x squared plus y squared equals r squared. And the thickness of the cross-section is delta x. Therefore, the volume of the cross-section is pi r squared times delta x. But r is y, so the volume is pi y squared delta x. the volume of the I-slice is pi yi squared delta x. But from the Pythagorean theorem, we see that x squared plus y squared equals r squared, or r squared equals r squared minus x squared. So the volume is pi r squared minus xi squared delta x. And so the total volume is the sum of all of the volumes. This is expressed using the Riemann sum. But as n goes to infinity, this Riemann sum is the definite integral from a to b of pi r squared minus x squared dx. Next, we find the limit of integrations a and b. But if we put the center of the sphere at the origin 0, 0, then all of the slices run from x equals negative r to x equals r. And so the lower limit of integration is negative r, and the upper limit of integration is positive r. We can just integrate from 0 to r by doubling the integral using symmetry. Using the fundamental theorem of calculus, the antiderivative of r squared with respect to x is r squared x, and the antiderivative of x squared is 1/3 x cubed. Plug in r, and then plug in 0 into the antiderivative. We then simplify 2 pi r cubed minus 1/3 r cubed, and the second term is 0. 2 pi r cubed minus 1/3 r cubed is 2 r cubed over 3. So the volume is 4/3 pi r cubed, which is what we needed to confirm. Next, we look at the volume of the pyramid of height h and the square base of size s. And so we slice this pyramid horizontally to obtain similar cross-section in the shape of a square because the base is a square. We label the side of this square x by x. Then the area of this cross-section is x squared. The area of the ith cross-section is xi squared. So the volume is xi squared times the thickness delta y. Note that in this case, we position the top of the pyramid at 0 with the y-axis pointing downward in the positive direction, so the thickness is delta y. We need to express x in terms of y, but we see that there are two similar triangles, the smaller triangle and the large triangle. The smaller triangle had the height of yi, and so the ratio of the similar triangles is xi over yi equals s over h. Isolate xi, we have xi equals yis over h. And so the volume is yis over h squared times delta y. Simplifying this, we have s squared over h squared, yi squared delta y. So the total volume is the Riemann sum, but as n goes to infinity, we obtain the definite integral. Y goes from 0 to h because the slices are from 0 to h. Using the fundamental theorem of calculus to evaluate this, we have 1/3 s squared h, which is the volume of the pyramid.